There we are. Lecture 6, looking at Cauchy sequences and completeness, and I started the recording late, so the definition of the Cauchy sequence is the same as the real numbers. Our first result is the same as the real numbers, and the proof is the same as the real numbers, so we just have to remember what the proof for the real numbers was. Okay, so let's take a convergent sequence. Fine, we'll start our sequence at M, I guess. This is a convergent sequence in the space XD. Okay. Well, that means that it has a limit. So let's let L be its limit. So let capital L be the limit of that sequence.
What's that?
That's great. Go watch your movie.
Open.
Now, we're going to get close to that L, and the point is, for any epsilon, we're going to get within epsilon of that L. So let's let epsilon be arbitrary. We know there is a capital N in the natural numbers, such that our distance between AN and L is less than, let's make it less than epsilon over 2. For all little n, at least capital N. Okay. Then, I'm just having a minor problem because I started our sequence at M up here, like Tau likes to do, but now I want to use the variable M down here. So I'm going to start our sequence at 1. It's just as general. Okay, then what I want to say is for all M and N, at least capital N, the triangle inequality shows us that the distance between AM and AN is at most the distance from AM to the limit plus the distance from the limit to AN. Okay, now those two distances are both less than epsilon over 2. So the total distance between AM and AN is less than epsilon. Okay, and that is what we needed to show to prove that the sequence is Cauchy. Okay, we found some spot at which our distances are always less than epsilon. Are there any questions about that? I hope when you reflect back on what we did last semester, you realize this is the exact same proof. We just we're using an arbitrary metric instead of the absolute value metric that we're used to. And we're in an arbitrary set, not the real line necessarily. Okay, now, we know on the real line, Cauchy and convergent are the same exact thing. Is that true in general? The answer is no.
Dr. Goddard, I have a
Yes.
quick question.
Yes.
So we have that this limit exists. Do we know that it's... Oh, never mind. We're talking about the whole metric space, not the... So the limit has to be inside of the set X. Was that one of our definitions earlier?
Yeah. So we've always got. It's a good question. We've always got some metric space that we're in, and all of our limits would have to be in that metric space.
Okay, because then because the distance metric wouldn't make any sense if it wasn't, right?
It's not that the distance metric wouldn't make any sense. Here, I think the example I'm about to do might clear things up. Okay.
Okay.
So the question is, do all Cauchy sequences converge? And the answer is no. Okay. Now, for an example, let's consider the sequence. This is always a fun sequence. We will take our sequence to be 3, 3.1, 3.14, 3.141, 3.1415, etc. Okay, I mean, so obviously I'm not going to write down a formula for that sequence, but I'm looking at the sequence of successive decimal approximations of pi. Okay. So the sequence I'm thinking about is going to converge to pi if we're in the real line. So viewed as a sequence in the real numbers with the normal metric, this sequence converges to pi. Oh, and not only does it converge to pi, it is Cauchy. Okay. Why is it Cauchy?
As we get later down, we can just, the difference is going to be, each decimal place, so we can make that as small as we'd like.
Yep. Or the easier answer is just, well, we agree it converges, right? And convergent sequences are always Cauchy. Okay. Viewed as a sequence in, now let's look at the rational numbers with the same metric. This sequence, is it Cauchy?
Yeah.
It's still Cauchy. It's still Cauchy because the terms still get close together. Or you could argue it's still Cauchy because it was Cauchy in a bigger metric space and restricting the metric space isn't going to change Cauchy-ness. Okay, but does it converge? Well, the answer is no. It does not converge. Okay, so how would you argue that it does not converge? There's a really hard way, and there's a pretty easy way. Yeah. So Roger says pi is irrational. Yep. So, but we need like one more line to make that a proof that this doesn't converge in the rational numbers.
You could say there just doesn't exist a value in our metric space for the sequence to converge to.
Okay, so I think that's going to the really hard way, because how do you know that's true?
I guess I don't.
I think when you go down that line of argument, you're actually going to end up trying to prove that pi is irrational. So let me just tell you, pi is irrational. Okay, so why couldn't the sequence converge? How about this? Why couldn't the sequence converge to something else in the metric space of the rationals?
Because it can't converge to two different values.
Yeah.
And it definitely converges to pi.
Yeah, so that's the argument, I think, here. This sequence can only converge to one thing. We know what it converges to in the real numbers, so it can't converge to something else in the rationals. If it converged to something else in the metric space of the rationals, then it would also converge to that something else in the reals. And it can only converge to one thing. Okay? So, does not converge in the rationals. Let's do one more. Viewed as a sequence in, let's take the real numbers, but now let's look at it with the discrete metric.
I have a question about the last one.
Yeah.
So, from like the definition of convergence, we can still get within epsilon of pi, even if pi is not in the metric space, right? For all
Sure.
epsilon.
Sure.
So there, like from the definition, why does it not converge then? Like,
Because
why
there's
can it
nothing.
not converge to something outside of the metric space?
That's just our definition of convergence. Your limit has to be in the space.
Okay.
You're just not
How
allowed.
I kind of think of it, the metric is only defined on the set that is the metric space. So asking what the distance to something outside of the set is doesn't make sense. It's not, your function breaks.
Mm-hmm.
So you can't even ask the question, I guess is how I think of it.
Yeah, I think that's a great answer. Yep. Okay, so what can you say about this sequence when we put the discrete metric on the real numbers?
Your conversion.
Yes, it's not Cauchy all of a sudden. Okay. Why is it not Cauchy? Well, in the discrete metric, the distance between two different numbers is 1. So the distance between any any two terms in this sequence will never get closer than 1. So it's not a Cauchy sequence. Okay? Because it's not a Cauchy sequence, it doesn't converge. Okay, a convergent sequence have to be Cauchy, so if we know it's not Cauchy, then we know it does not converge. Okay. Okay, good. That's our example. Now, the way to think about Cauchy sequences is they are the sequences that should converge. Okay. In some spaces they do. In some spaces, some of them don't. So now we're going to give a name to the sequences to the spaces where Cauchy sequences do converge. And we already know this name from the last semester, I think. Would anyone like to remind us? Yes, it's complete.
Professor, I also have a question.
Of course.
Kind of piggybacking off whoever was talking about the example of the previous sequence in Q. There is like a larger point to be made that the metric that we're using is kind of defined in R, but sort of reduced to Q.
Yeah.
Are there more, obviously not with any subset of R because we know that R is complete, but are there examples of more like screwy spaces where something more interesting will happen, where it's not just something that's like technically outside of the set, but if you were to extend the definition of the metric to something larger, like can you have a Cauchy sequence that is, for example, like bouncing between two values in a different space?
Oh. Okay, so a couple questions there. One thing is that no, if you've got a Cauchy sequence, it either it either converges or it doesn't converge. But one thing it's never going to do is oscillate. Okay, it's never going to flip between two limits. And what would it mean to formalize that? Okay, well, what it would mean to formalize, if you're an oscillating sequence, what that really means is that you've got one subsequence that converges to one limit and another subsequence that converges to another limit. Okay?
Oh, that's true, yeah.
Now, one of the results from today, later on today, is that if you're a Cauchy sequence, if you have a subsequence that converges, then the whole sequence converges. Okay? So you're never going to see that oscillation. Now, in terms of this thing between Q and R, what's going on there is that the real numbers are the completion of the rationals. Okay? So one way to actually construct the real numbers, which remember we didn't do last semester, right? We always said we're going to take the real numbers as given, and we'll just argue about them. We'll agree that they have the least upper bound property, and then we'll prove what we can. One way to actually build them is to say the real numbers are all the limits of Cauchy sequences of rationals. Okay. And you think about it, you're at least going to get all the real numbers if you do that, because every real number has a decimal expansion, so we can always do what we did to pi. We can take that Cauchy sequence of rationals, it'll converge to the real number we pick. Okay? So that's what's going on between the reals and the rationals. One is the completion of the other. Okay. Oh, and speaking of completions, the definition of complete, it's if and only if every Cauchy sequence actually does converge. Okay. Example we just did. The rationals together with the normal metric is not complete. Um, There's a theorem from last semester. The reals with the stated metric are complete. Okay. How did we prove that? Does anyone remember? Or what did we use?
We used the squeeze theorem, right? We squeezed rationals with a real between them, something like that.
I don't think so. I think what we used is the least upper bound property. Okay, I could be misremembering the proof that we gave because there's a couple, but I think we gave the really slick proof, which just uses the least upper bound property. Remember that property says every non-empty bounded subset of the real numbers has a least upper bound. Okay. Now, if you think about that, okay, that if we're going to prove other metric spaces are complete, the proofs are going to have to be a lot different from that, because in an arbitrary metric space, we don't have any notion of least or of upper bound. Okay. In our normal metric spaces, we don't have an order on the points like we did on the real line. So, our proofs for other metric spaces that they're complete are going to have to be different. Okay. What about a discrete metric space? So a metric space with the discrete metric, is that complete or not complete?
I would say it is complete
Mm-hmm.
because you're going to get just endless list of zeros or an endless list of ones eventually.
Endless list of
Or at
constants, yeah.
Something.
Mm-hmm.
Yeah.
Yep. Okay, good. So that's the second of the suggested problems for today that I'm going to give you, is to prove that discrete metric spaces are complete. And the whole point is that it's so hard to be a Cauchy sequence in a discrete metric space in the first place that then you're going to converge. Okay. Okay. So I don't think our next topic is subsequences. I don't think we've defined subsequences in our arbitrary context. So just so we're on the same page, let's write the definition. Okay. So definition. Suppose we got a sequence in a metric space.
Daddy, please jump in this.
Okay. Okay, and because Tal likes to do it, we'll start our sequence at M. Suppose this is a sequence in the metric space XD. And now let's choose some indices. Okay, the indices would have to be at least M. And then, you remember when we're choosing subsequences, we need these strict inequalities. We're not allowed to repeat an element. Then the sequence. Those are the indices of our subsequence. So our new sequence is going to be A sub n sub, let's say, J. And that is a sequence of our sequence A sub n. Okay. The only thing different from last semester is I said that the sequence is in an arbitrary metric space. Okay. Absolutely nothing else changed. And the metric doesn't feature into the definition of a subsequence. Okay? And now, the result that I alluded to earlier, proposition. If you got a Cauchy sequence, and it has a convergent subsequence, then the sequence has to converge to the same limit. Okay? So now let's write that. Okay, so if there is subsequence that converges to the limit, let's say L,
Battle, Dad. This battle. I can do it.
okay, so if you got a convergent subsequence, you converge to the same limit. Can I have that?
Okay.
Okay. I'm not going to prove this. I think the proof is a good exercise. It's not a long exercise. We can talk about it for a second. You assume you got a subsequence that converges to that limit. So at some point, so you fix an epsilon. At some point, the terms of your subsequence are within epsilon over 2 of the limit. Okay. Then the sequence itself is Cauchy. So you, for the same epsilon, at some point the terms are all within epsilon over 2 of each other. So then all those terms, they're within epsilon over 2 of something in the subsequence that is itself within epsilon over 2 of the limit. So all the terms are within epsilon of the limit. Okay? But that's a good proof to write. Okay? Questions about that? Okay, so let's just review what we've done so far. We've defined Cauchy sequences. We did prove that all the convergent sequences are Cauchy. We saw that not all Cauchy sequences converge. It depends on the completeness of the metric space. And then we proved our thing about subsequences. Okay, now for something completely different than last semester. We want to study the interaction of completeness and closedness. Okay, so Tao has a good word here. He says that a complete space is the word he uses here, the phrase he uses is intrinsically closed. That means if you embed your complete space into a bigger metric space, then no matter what bigger metric space you're embedded into, the complete set is going to be closed. Okay? And conversely, if you start with a complete metric space and you take a closed subset, that closed subset is itself complete. Okay? So these are two directions, and we'll prove them separately. And we've probably only got time for one of the proofs. So which one is more important? I think the second one is more important. So I'm going to state both of them and we'll prove the second. Okay? Okay. So this is going to say that a complete subset is closed. Okay, but we have to build up some framework around it to really talk about that. So we've got a big metric space XD. And now let's look at a subspace of that. Okay, remember subspace would be a subset Y together with the same distance function, but we restrict it to pairs in Y. Okay. If that subspace is complete, okay, now what does that mean? That means that any Cauchy sequence in that subspace converges in that subspace. Then Y is a closed set, so it's closed in the big space. Okay. You said we don't really have time to do a proof, but we can talk about it for a second. What does closed mean? We've got a lot of different versions of that definition. So now the one that I think is easiest here, you're closed if and only if you contain all of your boundary points. Okay. So to prove that Y is closed, let's take a boundary point of it. Okay. Well, what is a boundary point? It's a point so that every ball intersects both Y and its complement. In particular, every ball of our boundary point contains a point of Y. So therefore, if your point, here's your boundary point of Y. You take any ball, there is some point of Y in that ball. Okay? And now you can take a smaller ball. There's still some point of Y in that ball. And then you can take a smaller ball and so on and so forth. So what you can do is you can define a sequence of points in Y that is converging to your boundary point. And since you know that the subspace Y is complete, you know that sequence has to be converging to a point in Y. Okay, so what you did is you just showed that that arbitrary boundary point is a point of Y. Okay, like I said, we're gonna have lecture notes for this lecture, and I have written a full proof in the lecture notes, so you can look at those if you have any questions about that proof. Now, for the other half of this, we want to take a complete metric space and a closed set and argue that that closed set is still complete. And here we go. If okay, if the set Y is closed, and let's just be really clear on what we mean. We mean closed in the big metric space. Then the subspace is complete. Okay. So you take a big complete space, you take a closed subset, that thing is still complete. So notice, there's other ways to see this, but this result shows us that the rational numbers do not form a closed subset of the reals. Because if the rationals were a closed subset of the reals, then they'd be complete. And we saw earlier today that they're not complete. Okay? So, proof. Let's consider a Cauchy sequence in Y. So let A sub n be a Cauchy sequence in Y. Okay? Now, this is, therefore it's a Cauchy sequence in the bigger space. So the bigger space is complete, so this sequence converges in the bigger space. So, therefore, A sub n converges in the bigger space to some point. Let's call it capital L. Okay. Now, what does convergence mean? So therefore, or thus, for every epsilon, oops, I want to use R because we're going to be talking about balls here in a second. So for every R, I'm going to take the definition of convergence, put an R in there instead of an epsilon. So for every R, there is some capital N, so that the distance between AN and L is less than R for all little n, at least capital N. Okay. Now, where I'm going towards is I'm going to try and say that L is an adherent point of Y. So remember back to 2 lectures ago. So last Wednesday, we defined adherent points. Okay, what's the definition of an adherent point of a set?
The set along with its boundary.
Oh, okay. That's actually follows from a proposition.
Oh,
So I'm asking for actually what we used as the definition.
It's an arbitrary ball intersected with a set is not empty.
Yes. You look at a ball around that point, a ball of any radius around that point. It has a point of the set. So we've got that. Okay, that means that this for every radius, the ball centered at yes, L of radius R intersect Y is not empty. Okay. In fact, you might think it has a lot of points of Y because it has the entire tail of that sequence. But the tail of that sequence might just be one point repeated over and over forever. So who knows how many points it's got. Okay. Well, this shows that L is an adherent point of Y. Okay. Well, we assumed Y was closed. So, I guess I should write a little more after this. So L, because it's an adherent point, it has to be in Y. So remember, there's a few ways to remind yourself of all these definitions and how they're playing together. The closure of a set is all of its adherent points. And you're closed if and only if you're equal to your own closure. So we've shown that it's an adherent point, so it has to be, it's an adherent point of Y, so it has to be in Y. Well, because the limit of the sequence is in Y, so this means that our sequence converges in Y. So this implies that our sequence we started with converges to L in our subspace. And we might as well write the conclusion. We took an arbitrary Cauchy sequence in Y. We showed that it converges in Y, and therefore Y is complete. Okay. Are there any questions about anything today?
I have just a question for the quiz. Do we assume that the set of natural numbers contains 0 or not?
Oh no.
I have gold apple.
We went through this last semester. So last semester our book did not have 0 in the natural numbers. Personally, I always do.
Okay.
So what I'm gonna try and do this semester is make sure it never matters. Okay.
Okay.
So I guess the answer to that is you can do whatever you want.
Okay. Okay, thank you.
Yeah.
Oh my